Big Bang, from nothing to infinity. It has been 95 years since the birth of the Big Bang theory, and for these 95 years, scientists have been searching for the answer to one question. How is it possible that the sun, moon, stars, and galaxies we see today came into existence from a single explosion? Before talking about Big Bang, let's take a quick look at matter. You must have heard the phrase, we are all made up of atoms. Physics tells us that the atoms themselves are made up of three things: electrons, protons, and neutrons. If we zoom in further, even a proton is made up of three smaller components called quarks. If we go back 13.7 billion years, we would see nothing, because back then our universe did not even exist. But then suddenly, in this nothingness, an intense burst of light appeared, expanding about 2 trillion kilometers in just 1 second. And from this explosion, stars, galaxies, planets, and our Earth were eventually formed. But what exactly happened suddenly? Where did this light come from? Today we know what happened during the Big Bang, but we do not know what existed before it. Why we don't know? I will explain it at the end of the video. However, Einstein's theory of relativity tells us that before the Big Bang, our entire universe was smaller than an atom. Then something happened that caused this tiny point become unstable. And this instability was the starting of the Big Bang. Our universe operates according to some laws or forces. Whether we like them or not, we have to follow them. For example, if we jump, we will fall back to the ground. The opposite poles of the magnets will attract each other. Our universe is held together by just four fundamental forces: gravity, electromagnetism, strong nuclear force, and weak nuclear force. But 13.7 billion years ago, when our universe was smaller than an atom, these four fundamental forces existed together as a super force, which later separated. Before going into too much details, let's begin our journey through the Big Bang. The first second of the Big Bang is very important. In this 1 second, the future of our universe was determined. 13.7 billion years ago, instability began in this tiny point. At that time, temperature of this tiny point was 1 trillion degrees Celsius. This era of the Big Bang is called Planck Epoch. Planck is the smallest measurable unit of the time. At that moment, gravity separated from the other three forces. Separation of the gravity marked the beginning of the Grand Unification era. On one hand, due to extreme temperature, energy was continuously converting into matter and matter into energy. On the other hand, the temperature of this point was rapidly decreasing. As gravity separated, in the blink of an eye, temperature dropped so much that the strong nuclear force also separated from the remaining two forces, marking the beginning of the inflation era, the era of expansion. Because of the separation of strong nuclear force, this tiny point suddenly expanded trillions of times in size. This rapid expansion also caused the temperature to decrease rapidly. During the inflationary era, temperature dropped so much that energy permanently converted into matter, leading to the formation of different types of quarks. During the quark epoch, temperature of the universe had dropped to 1000 trillion degrees Celsius. This was the era when last two forces, weak nuclear force and electromagnetism, also separated from each other. By this time, the four fundamental forces had came into existence. The forces that have held our universe together ever since. As soon as last two forces separated, many leptons were also formed. Do you know how much time had passed since the beginning of the Big Bang? Half a second. After the formation of leptons, the next phase of the universe began, the Hadron Epoch. In this era, quarks combined to form hadrons, which include proton and neutron. During the Hadron Epoch, another major change occurred. Many types of quarks, leptons, and antimatter began to disappear over time. This meant that now the universe was dominated by protons, neutrons, and electrons, the three components that form atoms. By the end of Hadron Epoch, the one full second had passed since the Big Bang. After that, the era of nucleosynthesis began. In the next 3 minutes, temperature of the universe dropped to 1 billion degrees Celsius. Protons and neutrons started combining to form atomic nuclei. However, the universe was still so hot that electrons were not yet bound, preventing the formation of complete atoms. For the next 400,000 years, the universe continued expanding and cooling until the temperature dropped to 2700 degrees Celsius. Finally, the universe had cooled enough for electrons to combine with atomic nuclei to form complete atoms. Before this, the universe was just a chaotic mix of electrons and atomic nuclei, making it difficult for light to find its way through. But now, since the electrons were bound, light was able to move freely for the first time. This was the moment when the entire universe became illuminated for the first time. In the second video of the universe series, I mentioned a specific light, cosmic microwave background radiation. It was discovered in 1965. This is the same light that was emitted 400,000 years after the Big Bang. In the first video of the universe series, we learned that atoms have mass, and the greater the mass, the stronger the effect of gravity. After 400,000 years of Big Bang, atoms formed, and immediately gravity began pulling them towards each other. As atoms gathered, the pressure on the atoms in the center increased. For the next 100 million years, atoms continued clustering in different parts of the universe. Eventually, the pressure in the center of these clusters became so intense that nuclear fusion began among atoms. This led to the second illumination of the universe. This was the time when stars were born for the first time. Just as atoms were pulled together by gravity, stars also started attracting each other. For a long time, stars continued gathering in different regions of the universe, forming small groups called globular clusters. Over time, these clusters merged to grow larger. And finally, a billion years after the Big Bang, galaxies began to form. About 4.6 billion years ago, a star was born in Milky Way, around which a planet orbits, a planet we live on. At this point, a question arises. If atoms combine to form stars, stars combine to form clusters, and clusters combine to form galaxies, did this process stop here? The answer is no. Galaxies are still colliding and merging to form even larger galaxies. For example, when our Milky Way galaxy formed a billion years after the Big Bang, it was very small. For the next 2 billion years, our galaxy traveled alone in the universe until it collided with another galaxy, Kraken, increasing its size. A billion years later, the Gaia Enceladus galaxy collided with ours. A few 100 million years after that, Sequoia galaxy merged in. Another 2 billion years later, Helmi stream, and a billion years after that, Sagittarius dwarf galaxy crashed into our Milky Way, giving it its present shape. But this process hasn't stopped yet. Our nearest galaxy, Andromeda, moving rapidly towards us. In the next 4 billion years, Andromeda will collide with our galaxy, doubling its size. Do you remember dark energy? The mysterious force I mentioned in the second video of the universe series. We don't know much about dark energy, but we do know that it is in constant battle with gravity. Gravity pulls everything together, while dark energy pushes everything apart. If we look at smaller scale, like our local group, where 55 galaxies are located close to each other, gravity is winning. This is because the closer matter is, the stronger gravity becomes. But on a large scale, most galaxies are far apart. Because of this distance, gravity weakens, giving dark energy the upper hand, pushing galaxies even further away. As distance increases, gravity becomes weaker and dark energy grows stronger, causing the expansion to accelerate over time. This tells us that gravity is winning only in small clusters, like our local group, while on a cosmic scale, dark energy dominates. Dark energy is expanding our universe, and over time, its expansion has surpassed the speed of light. Now, before ending, let me answer the question I promised. What was before the Big Bang? The simple answer is, we don't know, and maybe we will never know. That's because our understanding of the universe relies on physics and mathematical formulas, which are based on these four fundamental forces. But before the Big Bang, these forces did not even exist, meaning at that point, our physics, maths, and understanding of the universe all fail. The next video in the universe series will be about solar system, and after that, we will explore the mysteries of the universe which are hard to digest, like space and time fabric, time dilation, gravity. Subscribe.